Chapter 8.2 is going to be kind of taking it a step down from what we've been doing currently with REF form or row echelon form and reduced row echelon form. Those skills are going to be very important and we're going to continue working with those, and these are going to seem kind of basic compared to those. But either way, these are all important still. Being able to add, subtract, and then multiply matrices. Those are the objectives of this section in operating with matrices. So the very first one that we have to deal with is adding and subtracting. So the process for doing this is that all you're doing is you're going to be looking at corresponding entries of our matrices and then adding them or subtracting them. So for example, if you were trying to find A plus B to get the sum matrix C, what we would want to look for is the entry in row 1, column 1 of our first matrix plus the entry in row 1, column 1 in our second. And that would be the entry 1, row 1, column 1 in our sum matrix. So here you can see down here, we want our corresponding parts, so -2 plus -4, that's going to get us our -6. This is our first row, second column entry, so we're going to look for the first row, second column entry here. So here we're going to add those and we're going to get 6. 4 plus 0 is going to get us 4. 3 plus -15, -12. -10 plus 2 is going to get us -8. 12 plus -4, because those are corresponding, we're going to get +8. 3 plus 6, and finding those columns, entries that match up, and -1. So there we have it, our sum matrix. Keep in mind, had this been a subtraction, then what we would want to maybe do is change it to positive and then negate all of the signs in here. So just be careful that we transfer that subtraction sign if this does happen to be subtraction. The thing that I want to visit now are the requirements of adding and subtracting matrices. If you are looking at this, what you're going to find out is, hey, if they do not have matching orders, you cannot add them. So in order to add, we need to make sure that the order of the matrices being added are the same. Okay, note how we had a 3 by 3, A was a 3 by 3, and B was a 3 by 3. We needed that because if we're going to be combining corresponding parts, there's going to always have to be a corresponding piece, right? That should be a 3, sorry. Alright, now for some properties dealing with matrices. Here are a couple that I do want you to make note of. So you can ask yourself, hey, do you think that the operation for adding and subtracting matrices, do you think that's commutative? Well, here's where you're going to want to play around with this a bit. So on this next page, I have this very same matrix that we just did, you'll note. Okay, so the thing of a mathematician is they always want to give it a try, and if they start to see patterns of things, hey, yeah, this is working over and over again, that's when theories can be born, and that's when proofs can also be developed, so that we can say, yeah, always, when you add two matrices, then yes, it doesn't matter the order in which you add. So let's go ahead and try this, and just give it a first step. So let's take our corresponding parts, or our corresponding entries, add those together. 6 and 0, we're in row 1, column 3 entries now. We're going to get 4, and you can see, oh yeah, this is definitely working out to be the same. This is where you could keep working with this and seeing, alright, are there any counter examples? But what you will find is there are no counter examples, and then you can maybe start to make those thoughts of, well, you know, all we're doing is we're adding corresponding parts, and since addition of real numbers is also commutative, then since we're just really adding these corresponding parts, it won't matter which order we add these matrices in. So this one's definitely a yes. Is it commutative? Yes, they are. Can we do the associative property? Go ahead and check this out, since you are mathematicians, and you can try to form some theories and thoughts, but yes, they are. An identity matrix for adding and subtracting is going to be an all zero entry of the same dimension. The next operation we want to focus on is scalar multiplication. Scalar multiplication is going to be just taking a constant number and multiplying it that's on the outside of matrix, like this, 2 times a matrix A, 2 times this matrix A. We're going to take that and just multiply that to each and every entry inside there. Again, play with this if you want. Doesn't matter what order, but we're going to say commutative property, yes, we still can claim that a number times a matrix equals the matrix times the number. Associative property, doesn't matter what order we do these, and we're going to say, again, it won't matter, so the associative property does apply, that we could say that those are equal. And then the distributive property is also applicable here. So the operation process, let's go ahead. This one's going to just be where you take that constant and multiply it to every entry. So we're going to get -2, we're going to get 6, 8, and -10. That's scalar multiplication. The last operation that we have is going to just be multiplication of two matrices. This is a little bit more of a confusing process, but you're going to really understand this by seeing it with an example. Not so much maybe the written out process here, but the entry of the product matrix, entry C1, 1, so row 1, column 1 entry, is the result of summing row 1 of matrix 1 times the column 1 of matrix 2. So we're going to take each of these entries of the row in matrix 1 and the column entries in matrix 2, and we're going to multiply them and then sum them up together. So the requirements, let me go through this first. So you can only multiply if the number of columns in matrix 1 is equal to the number of rows in matrix 2. Note our example down below. What we have is a 3 by 2, right? Because a row, 3 rows times 2 columns. Okay, and then this matrix B, we have a 2 by 2. So are we going to be able to multiply these? Well, as a requirement states that this is our column in matrix 1, right? These are the number of columns in matrix 1. There's 1, 2 of them. And this is the number of rows in matrix 2. So does the columns in matrix 1 equal the number of rows in matrix 2? They sure do. So what we can go ahead and do is multiply these. The one other thing that results from this kind of lineup to check that, yeah, those matched up so I can multiply, is the outside numbers end up being the dimensions of the, or the order of the product matrix. So the outside numbers are the dimensions, or the order, it is the order, of product. So can it be multiplied? Yes. And then the new dimensions, therefore, are 3 by 2. Okay, so this thing, what I am fully expecting is 3 rows. So a C1, 1, and then a C1, 2, a C1, 3. So 3 rows and then 2 columns. That's 3. C, this is column row 1, column 2, C1, 2. Sorry, this is 2, column 2. This is row 3, column 2. So we just need to find out what are those equal to. So the idea here is, like I said here up at the top, is this entry right here is the mix of taking my row 1 times my column 1 and summing them up together. So it's a little bit confusing because you have to kind of tag this -1 to this 1, this 3 to this 0. What I'm going to show you is I'm going to take this matrix and I'm going to kind of flip it on its side. So we're going to flip this just like this. So here, this C1, 1 is when I took that row 1 to this column 1. So -1 times 1 plus, and then 3 times 0. That is going to be my C1, 1 in my products matrix. The next entry here would be taking that same row 1 multiplied by column 2 in that second matrix. So I'm just going to move this over, okay, and we're going to be lining that -1 to that 2 and that 3 to that 7. So here we're going to get -1 times 2 plus, and then this 3 times 7. So now that I'm done with that first row, I'm going to actually erase this. And what we're going to do is we're going to look now at the second row, because C2, 1 is taking that second row of that first matrix times the column 1 of my second. So here we're going to have 4 times 1 plus, and then negative 5 times 0. And then we're going to move that 4 to that 2, so we're going to have 4 times 2 plus negative 5 times 7. I kind of ran out of room here. Okay, and then finally, I'm done with that row 2, so now I'm going to move on to row 3, and that's exactly what this is saying. Take row 3 times column 1 in that second matrix and that first matrix. So we're going to sum those up. 0 times 1, 0 times 1, plus 2 times 0. And then take that times that 2, 0 times 2, plus 2 times 7. So our final matrix that's going to result is just now simplifying what we've got here. So that first one's going to be negative 1, because this is just going to cancel out. I'm going to put that back up now, too, so I can just kind of see exactly what I've done here. So this next one was negative 1 times 2 and then times 7. Sorry, that's 3 times 7. Okay, so we had negative 2 and then plus 21, so this would have been 19. And then we have 4 times 1, which is 4 plus 0, so this is going to be 4. This would have been 8 plus, and then negative 35. We're going to get negative 27. Here we're going to get 0 and 0, so 0. And then we're going to get 0 plus, and then 2 times that 7 again, so we're going to get 14. I would say go ahead and fill this in here. I'm not going to do it again, but you can go ahead and put that right there. Commutative property. Here's where, again, as a mathematician, you would be like, well, are they commutative? Things would suggest so, because, hey, the commutative property addition stuck with real numbers and then also transferred to the matrices. Does that still work with, we know that you can take 2 times 3, and then that's the same thing as 3 times 2. Will it work? So the first thing to check is, can we multiply these? And you might run into a problem, because when you try to put up the row against the column, you're not going to be able to. Yeah, you'll be able to take this 1 times negative 1, this 2 times 4, but what about that 0 there? This is a 2 by 2 and a 3 by 2. These don't match up, so it cannot be done. Okay, so this is actually not going to work. So going back here, what we can say is commutative property, does it exist? No, it does not. Okay, associative property, you can play around with that, but yes, this one actually does. And then distributive property, so does this one. One more definition here is we have identity matrices. An identity matrix is a square matrix, and this is multiplication. This is for multiplication. Oh, what the? Okay, so anyway, I'm not going to touch it because it keeps doing that. Multiplication. It's a square matrix with the diagonal of 1s and all other entries of 0. The notation is just I. So what I would like you to actually look at is this slide right here. And we're going to play around with this. Matrix operation identities. So all 0 entries for the same order for addition. When we're talking addition, typically what we're used to is for addition in real numbers, you have 0 plus 2, it just equals itself. It keeps its identity. Well, let's go ahead and line this up with an all 0, 0, 0, 0, 0, 0, 0, 0, 0, 0 of a 3 by 3, just like this one is. So now that they're the same dimensions, we can go ahead and add them. And what you're going to find is that when you do add those corresponding parts, we're going to get the same exact matrix, right? So that's why this is called our identity addition matrix. All zeros, same dimension as whatever the matrix is that you're working with. Okay, so there's that. Alright, so now for multiplication, when we're talking multiplication, in the world of real numbers, we had the number 1. 1 times 4 would just keep the identity, right? It would keep the identity of whatever you were multiplying 1 by. Alright, now what we're going to be doing is setting up a RREF form, or a diagonal of 1s, with all other entries of 0, and a square matrix. Since this is a 3 by 3, we would also need a 3, because we would have to have those line up by, and then whatever this is, we're going to have to make it the same so it's a square. So here we would have a 1, 1, 1, 0, 0, 0, 0, 0, 0. What I would like you to do is go ahead and try to multiply those out. What you will see is when you do this, you're going to have a negative 2 times a 1 plus a 0 times a 0 plus a 4 times a 0, so what's going to happen is you're just going to get negative 2. Okay, then we're going to take this row, because this is going to be, we're expecting another 3 by 3 here. Okay, and then this C1 in row 1, column 2, we're going to take that row 1 times this column 2, and what you're going to get is negative 2 times 0, so that wipes out. 0 times 1 wipes out. 4 times 0, we're going to get a 0. And then finally C1, 3 is when you take that row 1, because that's what this is indicating, times column 3, because that's what that 3 indicates. We're going to take negative 2 times 0, 0 times 0, so those wipe out. 4 times 1. So what you can see is we're getting the same exact thing that we started with. So you might be wondering, does it have to be a square matrix and this will still work? No, it doesn't. Had we had something like 1, 1, 2, 2, 3, 3, so this is a 3 by 2 matrix, because 3 rows, 2 columns, you would just have to take it up against a 2 by 2, right? So we would make that identity matrix just like that. There's my diagonals, and all of those other numbers besides that diagonal are zeros. Go ahead and try multiplying that, but what you will find is they will be getting you the same exact matrix. Alright, your homework for this assignment is through 42. There's your homework.